In this video, we are going to convert decimal to binary number. So here I have considered one example. Suppose the number is 100, which is this one, and we have the following representation on the screen. The binary equivalent of this number 100 is 1100,100. But the question is from where these values have come. So let us see that. Children, this value, which is 1 here, actually it represents 2 to the power 0. And since the base of the binary number is 2, so everything will be in terms of 2 to the power something. So here it is 2 to the power 1. It is 2 to the power 2. And this one is 2 to the power 3. 2 to the power 4, 2 to the power 5, and here it is 2 to the power 6. Children, this bit of that binary representation is MSB, which is most significant bit, and this bit, which is 0, is the least significant bit. So if we have this representation, if anything, if we are recording 1 here, if we are writing 1 here, it is simply equivalent to 2 to the power 6. So that's why here the value is 64. And if we are recording here 1, it means it is 2 to the power 5. So it simply means 64 plus 32, which is 96. And if you subtract 96 from 100, then you will get only 4, which is this one. And now here, since so at this place where 4 is written, we have recorded 1, and rest of the bits have got 0. So if we add all these values, which is 64, 32 and 4, it is the total sum total is 100. So the binary representation of this 100 is 1100100. Now so I'm just going to give one more example here. So please see. So children, here it is one more is just wait. See. Children, suppose we are considering any other number, and initially suppose the values are, all the values are 0. Suppose we have considered, we have made all these values 0, and suppose here the value is 57. So I would like to convert this 57 into binary. We cannot record 1 here because it is equivalent to 64. So then what we will be doing, we will record 1 here, which is equivalent to 32. So now 57 minus 32, which is 25. So which is 25. Okay. Now at this place, now 25 is still more than this value 16. So here if we record 1 here, it is equivalent to 16. So 24 minus 16, which is equivalent to 9. Now we can do one thing, that if 9 is still more than this value, which is 8, 9 is still more than this value, which is 8. So what we can do is we can record 1 here. Okay, so we have recorded 1. So now what is, if we subtract 8 from this, we will get 1. Now 1 is less than 4, so we cannot record 1 here, because if we are writing 1 this at this place, it will be equivalent to 4. That's why we cannot write 1 here. So now what we will be doing, we will move to the next step, which is 2 here, and 2 is still more than 1, so we cannot write 1 here, because it is equivalent to 2, which is more than 1. So here what we will do, we will be writing 1 here. Now it is equivalent to 1. So if we subtract 1 from this, you will get 0. So the binary representation for 57 is 1 1 1 0 0 1. So this is how we have converted binary to decimal. Now I am just going to consider one more example, and before that I would like to make all the entries 0 here. Just have a look. So here children, suppose the value is 90, not 90, the value is suppose 85. Okay, so 85, in order to convert 85 into binary, what we can do here, we can simply record 1 here, because 64 is less than 85. So 85 minus 64, which is what, which is 21. So which is 21. Okay, so now we proceed to the next step. So lower significant bit, which is 32, and here this 0, I'm just talking about this 0. So we cannot record 1 here, because it will be equivalent to 32. So what we will be doing, we will be recording 1 here. Okay, so when we have recorded 1 here, it is equivalent to 16. So here minus 16, which is equivalent to which is the remainder is 5. So now it is the remainder here, 5 is left, and we cannot record 1 here if we move to the lower significant stage. So here we will be getting 8 if we are recording 1. So we will not be recording 1 here. It is 5. We will move to the next significant stage. So which is this one. So here, which is this one. So here we will be recording 1 here. So in that case, if we are recording 1 here, it is equivalent to 4. So minus 4, which is 1. Now 1 is left. We now move to the next significant bit, which is 0 here, and if we record 1 here, it will be equivalent to 2, you can see. So we will not be recording 1 here. We will move to the next lower significant bit, so which is 1 here, and if we record 1, so subtract now minus 1 equals to 0. So the binary representation of 85 is 101 01 01. So this is what, and the same logic we are going to implement. Now see how to implement this. Children. So we need to define the whole class for this. So for that, now here you start implementing the body, defining the code here. First of all, you just define this function, this opening and closing brace of the class. Children, this display function only prints the number, and this within this print function we will be actually printing the binary equivalent. So for that I have taken one parameter also, but we don't need to take the parameter. We have already defined the instance variable. So first of all, define this package so that we can use a scanner class, and here this is the constructor. So this is for initializing this instance variable num, and here we have to just display the number is, which is num. The number is num, and after that here we need to display it. So here we need to calculate or generate binary equivalent here within this function. Okay, fine. Now the main method, and in the main method we have taken this n, scanner ss, new scanner, and here now enter the number here, so which is n, which is ss.nextInt, and now just create the object of the class, new decimal to binary, passing the number here, and after that I'm just going to display this function, and after that I'm just calling this function print, and this function print will definitely print the binary equivalent. Okay, now after this I need to define the function body of print this function print we need to define. Let us see whether this much part is working or not. And here inside function print, okay. So children, suppose the number is 100. Yes, the number is 100 and inside function print, this is working. Now one of the important question is, children, we have to identify that how long, suppose the values are like in terms of 2 to the power are 64 and then 32 and then 16 and then 8, 4, 2, 1. Suppose the number is 100, so how long we have to consider? Suppose we have to consider up to 64 only, because if we move beyond 64 we will be getting 128, which is more than 64. So somewhere we have to take the pause. So we have to find out the maximum value in terms of 2 to the power, up to which value we have to move. So this is one of the important question. So for that we have to do one thing. First of all, just take one value p, and initial value of p is 1. So now what we have to do, while this p is less than or equals to this num by 2, till it is up to this place, we have to multiply this p by 2, and after that here we can print the maximum value is, which is p. Now see that, suppose we have got 100. Here you see that the maximum value is 64 has come. So because beyond this value we will be getting 128, which is more than 100. So unnecessarily we need to have 0 there, no need. I want that most significant bit must be 1. So if we are going to represent any number and if the most significant bit starts from 1, that is fine. That will be the best thing. So here with the help of this code we will be getting this maximum value in terms of 2 to the power. So now here I'm just going to print the binary equivalent. The binary equivalent, the binary representation. The binary number is, okay. Now the binary number is here we have to see the binary. So for that what we need to do, we need to start another while loop, and it will go till it is more than 0. Till it is more than 0 or till it is not equals to 0. So this is what we have to do. So here we just start a loop with this one, and if the number is better we make the duplicate copy of that. So here, so that the original number is not lost, and here we need to write if copy is more than or equals to p. If copy is more than or equals to p, then what we need to do is just record here, just system.out.print it is 1, and here num is equals to num minus p, and if it is not the case then here we need to write which is here we need to print 0 and nothing else, and after that here we need to just divide this number by 2. Divide this number by 2. So this is what we have done. So till now just see that. So suppose the number is 100, and now you see it is coming like this, it is not like this. So the binary equivalent is this one. So children, here the mistake which I have done is just it will be copy, not num, because here I am just using the duplicate copy of num. I don't want to modify this. So you see that the equivalent binary is 1100,100. So here better we change this to equivalent. The binary equivalent. Okay. The binary equivalent is which is suppose 125 it is, and the binary equivalent is this. Here if it is suppose 25, if it is 31, 5 times 1 will come, fine. And if it is 64, 1 and then 6 times 0 will come, excellent. So it's coming like this, but I would like to explain it one more time to them. Here I would like to explain, suppose we have taken the number 75 and initial value of p is 1. So what will happen? So while this p is less than or equals to 75 by 2, so till it means till this part it will go. So something if it is not 75, it will be easier for us if we consider this number as suppose 80. So here if it is 80, so the loop will go up to less than or equals to 40. So initially it is 1, then it will become 2, and then it will become 4, still less than 40. It is still less than 40, then 8, then 16, then 32, and then 64. So when the value of p becomes 64, this outer loop terminates. After that, what happens? This p is 64, and which is now it is more than 0. So what is the value of copy? Copy is 80. Okay, so 80 is greater than or equals to 64. Fine, this condition is true. This is 80 and this p is 64, which is, this condition is true. So 1 will be printed on the screen and 80 minus 64 will happen. So it is 80 and minus 64 will happen. So here it is 6 and here 1, 16 is left. So what will happen? So this at this moment this else part will not execute, but this p will become, this p was 64, now it becomes 32. Now this p is 32 and this copy is 16. This condition is false. So what will happen? After that, here 0 will be printed. And now this value, again p will get divided by, so now this value becomes a 16. And this 16 is more, this 16 is, children, here at this moment of time, this copy is 16, and when we subtracted 64 from 80, it is 16. It is this p is also 16, this copy is 16, this condition is true. 1 will be printed again. So here what will happen? This 1 will be printed again. This copy will become 0. This copy will become 0, else part will not get executed. The value of p is 16. Now the value of this this p will become 8 now. So this copy is 0, this is 8, condition is false, 0 will be printed. Now this p will become 4, again 0 will be printed because copy is 0. So every time this condition will become false now. So this is so again 0 will be printed. It is 8, it is 4, again 1 0 will come, and it is for 2, and again 1 0 is come, which is for 1. Now p will become 0, loop terminates, and this is the equivalent binary representation, which is 80. So if you add, children, just check this, it is 1 2 4 8 16 32 and 64, and 64 this one, and plus 16 this one. So if you add these two, you will be getting 80. So this is what binary equivalent of the decimal number which you have entered, and this is an excellent method of converting decimal to binary. And I hope you have enjoyed this video. Thanks for watching.